So for all of the equations that I derived in the first two parts of the linear drag thing, I derived those same equations in the scenario where there's no drag, and I have them both graphed here. Well, at the moment I only have the no drag scenario graphed, but I have the other one up here. So the y variable is going to be what we're looking at, so in this case it's velocity in the x direction, and then the x is going to be the time taken. And in terms of the values, I have the mass. We're using the values from the golf ball, so the mass is 0.046 and k is 0.01. So starting off with velocity in the x direction, you can see when we have no drag, we assume that the velocity is a constant. It's going to be u, the initial velocity, multiplied by the cos of the angle, which I have called a here. And you can see it's just a straight line that goes on forever. It never ends. We assume there's no acceleration in the x direction, and then it's just going to keep going on forever and never going to change. You can see if I change the angle, it gets higher, and if I make it go really high, it gets lower. And this makes sense. If we launch it at an angle of 0 degrees, that means it's going straight, so that's going to give us the highest velocity in the x direction. But as we increase the angle to be more upwards, then there's less velocity in the x direction, because more of it's going into the y direction. And you can see if it's shot at 90 degrees, there's nothing in the x direction, because it's just going straight up. And obviously, if we change the initial velocity, it's just going to go up, and if we decrease it, it's just going to go down. So now if we look at the equation with drag, I'm going to turn off this blue line for a second. You can see it makes a bit more sense when you think about what actually happens when you throw a ball. So you can see after about 20 seconds it's pretty much 0, so it's pretty much stopped moving after 20 seconds because the air has just kept slowing it down. And the angle doesn't really change much. It's kind of the same as the other one. It just changes what it starts at, because again, if it's at 90, it's going straight up, there's nothing in the x direction, and it's at its highest if it's at 0, because it's going completely horizontally. And if we increase u, it's just going to start up higher, but you can still, and you can see it keeps going for a little bit longer, but it's honestly not much of a difference. If we compare them, you can see it just levels off, it just goes down, and then this one just keeps going on straight. So it's not very interesting. But if we look at displacement in the x direction, this is when it gets a bit more interesting. So again, y is going to be how far it's traveled in the x direction, and x is going to be the time taken. So you can see it just keeps going up forever, because the distance is always increasing. That makes sense. And it's increasing at a constant rate. It's just a straight line. So if we make the angle 90, you can see that displacement doesn't change at all, because it's going straight up. Nothing's happening in the x direction. But if we make it 0, you can see it's as steep as possible, which is when it's only going in the x direction. So let me just put that back to 45. And again, with the initial velocity, that'll just make it steeper, because the displacement's obviously going to be increasing at a quicker rate. If it starts at a quicker velocity, velocity is the rate of change of displacement, so the displacement's going to increase more if we have a higher velocity. So if we compare that to the other equation with drag, this is very interesting. So I'm going to get rid of the no drag scenario for a second. So you can see we start at 0. So this is with initial velocity 10 out of 45 degrees. So we start at 0, and then we start going up, and it's at this is a pretty steep slope. But you can see the slope actually decreases until it eventually levels out. This makes sense, because remember, the drag is proportional to the velocity. So as the velocity decreases, the drag decreases, which means the rate at which it slows down decreases until it gets to more or less straight over here. You can see it kind of levels out at about 32. If you fired it with an initial speed of 10 meters per second at an angle of 45 degrees, it'll stop in the x direction at about 32 meters, 32.5 meters, because you can see it doesn't increase beyond this anymore. And you can see if we decrease the angle to be 0, that's obviously going to be the farthest scenario, because it's only going in the x direction. And again, if we make it 90, it's going to be a straight line, because it's not changing in the x direction, because it's going straight up. And if we increase the initial velocity, it goes further. And then if you compare it to the no drag scenario, you can see at the start they're pretty much the same. It's just as more time passes, they start to separate out a little bit, which makes sense, because at the start the drag hasn't had time to really kick in yet. But after a few seconds have passed, the drag's already taken away a good bit of the velocity. So now let's have a look at velocity in the y direction, and this is the no drag scenario. So this makes sense. So when you start off, you start at, we're saying, a velocity of 10 meters per second at an angle of 45 degrees. So that puts us about here in the y direction. I guess if we make it the angle 90 degrees, that's when it's going to be at its highest, because this is only going in the y direction now. So if it's only going in the y direction and we fired it at an initial speed of 10, then you can see it's going to start up at 10, and the velocity is going to decrease. It's decreasing at a rate of 9.8 meters per second squared, because the gravity is making the velocity reduce by 9.8 meters per second every second, until eventually we get into the negative velocities down here, and it just keeps going on forever, because it never knows when to stop, because we didn't tell it to stop. It's just a straight line that goes on forever. But we know in actual fact, eventually it will reach terminal velocity, and at that point it'll stop accelerating, and the velocity will be a constant. And you can see as we change the angle, if we do 0, it starts at 0, which makes sense, because that means it's only going in the x direction. And as we increase the initial velocity, it starts at a higher velocity, and then it just keeps going down. Now if we look at the drag scenario, this is very interesting. So you can see at the start, again, they're basically the same, but then as we go down, it actually starts to level off around 20 seconds, which is, remember, that's kind of when it started to level off for the x direction as well. And then one of the really cool things is you can see the point at which it levels off here. Remember, the y is going to be the velocity, what we're looking at, and it levels off at a velocity of about minus 45. And remember, when we calculated the terminal velocity, we calculated it to be about 44.6 or something. So it's very close to the terminal velocity that we put in. Obviously, we kind of rounded it off, which is why it's not exact. But it's very interesting that you can see it just keeps decreasing until it reaches that terminal velocity that we calculated earlier. Now we're looking at displacement in the y direction, and you can see this is the no drag scenario. It's completely parabolic, so it just goes up, and then it reaches the top point here at 2.88 seconds, then it goes down, and it finishes here at 5.77. So one thing I want you to notice is that 2.886, that's half of 5.772. So when it reaches its maximum point, it's halfway through the total time. Remember, the x component is the time. And it just goes all the way up, and then it starts going down, and it keeps going down forever. Same with the last one. Except because the velocity is getting bigger and bigger, that means the displacement's getting bigger and bigger, so you can see the line keeps getting steeper and steeper because the displacement is increasing as the velocity is increasing. Now if we look at the version with drag, think about what you think would happen. So remember, the drag opposes the motion of the object, so what changes do you think that's going to make? Well, if we have a look, you can see it reaches its maximum point isn't as high, which makes sense, because as you're going up, the velocity is decreasing not just because of gravity, but it's also decreasing because of drag. So you can see we reach the ground at about 4.914 seconds, but when we reach the maximum point, that's 2.24, and 2.24 is not half of 4.9. It doesn't seem like much of a difference, but I'll show it in a second. As the velocity gets bigger, this gap actually increases. So at first, the no drag scenario is further out than the drag scenario, and that makes sense, because it was being slowed down on the way up. Then as we're going down, the force of drag is actually opposing the force of gravity, because now the velocity is downwards, which means the drag is upwards, which means that the acceleration is actually smaller on the way down, which is why it eventually catches up to this blue line and actually eventually surpasses it. And if we increase the initial velocity to be something like 100 meters per second, which is very, very fast, you can see the difference is even bigger. And that makes sense, because drag is proportional to the velocity. So if the velocity is bigger, then the gap is going to be bigger, because the drag is going to be bigger. And as you can see here, it reaches the ground at about 10.6 seconds, but it reaches its maximum point at about 4.3. So that gap has actually increased. But still, for this blue one, it reaches the maximum point at 7.215, and it reaches the bottom at 14.431. Again, so that stayed true. The last one we're going to look at is this Cartesian equation. So this is the exact trajectory that the ball would follow if you were to throw it. So in this case, the x actually represents the x displacement, and the y actually represents the y displacement. So if you were to throw a ball without drag, this is what would happen. It would start here, and it would go up, and it would fall back down. This is completely parabolic and symmetric. So you can see at the highest point we've traveled 5.102 meters in the x direction, and at the end we've traveled 10.204, which is exactly double that. So we know that at the maximum point we've done half of the journey. So that means it's symmetrical, and it's exactly parabolic. Another thing we can notice is that as we change the angle, so if we have it really high, remember it just goes straight up. So obviously when it's 90, it's not going to work. So if I have it like 80, 89, you can see it pretty much just goes straight up. And if we have at 0, it's going to go pretty much completely horizontally. And remember earlier we calculated the sweet spot to get the maximum range is 45. So you can see as we get to 45, it keeps getting bigger and bigger. And then once we surpass 45, it starts to get smaller again. So now if we look at the equation with drag, this makes sense. It doesn't travel as far because the drag is slowing it down. And if we have a look at whether it's parabolic, so the highest point is 4.41, but the end point is 8.403. So 4.41 isn't half of 8.403. So that means it actually travels further in the x direction in the first half, and then it travels less in the second half, after the maximum height. And if we make the initial speed bigger, we can see this difference actually increases by quite a bit. So now we can see the maximum point is 32, basically 33, but the ending point is 57. So that's definitely not half, and you can see even more clearly here that we travel further in the first half than the second half. And that makes sense, because once we get to the second half, it's been slowed down by drag a lot. Whereas in this scenario, we travel the same distance because there is no drag slowing down the x direction. Now bear in mind this is for the golf ball, so let's see what happens if we put in the basketball values. So this is with the values of the basketball, so the mass is 0.625 kilograms, and the value of k that we got when we calculated the terminal velocity was 0.54. See, there's a massive difference here. So you can see when we had the golf ball values, it was up here at 9, but once we put in the basketball values, it gets way smaller down here. So I don't know if this is unrealistic, but it seems kind of weird that it's way smaller, although it kind of makes sense, because when you think about it, basketballs aren't designed to be as aerodynamic as golf balls, because the basketballs, they're not traveling as quickly, which means there's actually less drag. So maybe because the velocities aren't going to be as high, there's going to be less drag, which means that they don't actually design them to be as aerodynamic, so this is actually true. Now remember, when I looked up the terminal velocity online, it was actually different. So when we calculated k using the online number, it was about 0.31. And you can see it actually goes further, so this is more similar to the golf ball scenario, and I think this actually makes more sense. So you can see it's 3.75 and this is 6.7. So it's not parabolic. And if we increase the initial velocity, you can see the gap gets even bigger between them. So yeah. But in reality, I don't think anybody could really throw a basketball at 43 meters per second. It would kind of be more down near 18, I'd say. And it kind of makes sense here at 18. But I don't know. I could have made a mistake. I think I might have. So if you know where I made the mistake, please tell me. And then the last thing I wanted to look at is, so this is back to the golf balls things. We want to see what the best angle is. So I tried calculating it numerically, and it's really difficult. But thankfully, we can just graph it, and we can just play around with the angle, to find out. So right now it's at 45, and as you can see, it actually gets bigger if we go a bit further down. So the optimum angle isn't actually 45 anymore. So if we just zoom in really close so we can get very accurate, you can see it's about 42. Yeah, so you can see at 42, if I go down, it gets shorter, and if I'm at 42 and I go up, it also gets shorter. So it's about 42 degrees for a golf ball, although bear in mind this isn't actually accurate, because the spin of the golf ball actually has an effect on how far it travels in the real world, and I did not take that into account. And remember, this is linear drag, and linear drag isn't actually very accurate. It's quadratic drag, which is way harder. That's the accurate one. So this isn't a very accurate model, but we can see that the best angle has changed. Now for the basketball, if we do it for the values of k that I calculated, 0.54, we can see the optimum angle is actually less than 42. You can see if we go further down, it keeps getting longer. So here it's actually more like 36, I think. Yeah, you can see when we're at 36, if we go up, it gets a bit bigger, about 36.2. If we go up, it gets smaller. And if we go down, it also gets smaller. So I think 36.2 is about the optimum angle for a basketball using the value of k that I found with my terminal velocity. Using the value of k from the internet's terminal velocity, which was 0.31, see the best angle is, it's actually higher. If we go up, it's about 40, it looks like, because when we're at 40, if we go higher, it gets smaller. If we go smaller, it gets closer. So yeah, it's about 40 with the other value of k that we found, using the value of the terminal velocity online instead of calculating ourselves. So that's an analysis of the equations of motion with linear drag. Obviously they're not going to be super accurate because they don't take spin into account, but that's even more complicated. So let's see if that changes the answer for the other problems we were trying to solve earlier with no drag. Let's see if that changes the answer by much.